Hey everyone, welcome back to the channel. In this video, we are going to dive deep into Bias-Variance Tradeoff, an essential concept in machine learning, and we'll be using the California housing dataset, which is a regression task, to demonstrate how different models with varying complexity behave in terms of bias and variance. We'll also walk through the code to see how the trade-off in action. So let's get started. Before we jump into the code, let's quickly recap what bias and variance mean in the context of machine learning. So the bias is the error introduced by approximating a real-world problem with a simpler model. A model with highest bias does not capture the complexity of the data, resulting in underfitting. On the other hand, variance is the error due to the model being too sensitive to small fluctuation in the training data, leading to overfitting. So the bias and variance trade-off is the challenge of finding the right balance between the bias and variance. A model with high bias performs poorly because it's too simple, and model with high variance perform poorly because it's too complex. The goal is to minimize both and build a model that generalizes well to unseen data. Now that we understood the theory, let's look at how this play out in the practice using the California housing dataset, which has the continuous target value, perfect for demonstrating regression. Let's start by loading the libraries and housing data set from scikit-learn. So let me load the libraries. Next, we load the data. We load the data set and split it into training and test sets. Now let's analyze the regression models, the linear regression and decision tree regression. So these are suitable for the regression task. And let's see the shape of X train and Y train dataset. So we have 16,000 rows and 8 features and similar target value. So we'll train these models and evaluate them using the mean squared error, MSE, which is a common metrics for regression tasks. The goal is to see how each model performs on both the training and test data. So in this, I'm looping with the model, fitting the data with X train, Y train, creating the predicted values, and then calculating the mean square error. So if I run this, so I got the mean linear regressions MSE and the decision tree MSE. So this we get the MSE value for each model, which help us to understand how well they fit the data, right? Here we might see after running the code, the linear regression will likely show relatively high MSE on both the training and test dataset, indicating it has a high bias and is underfitting the data. The decision tree regression, on the other hand, may perform very well on the training set, right? But poorly on the test set. So it indicates high variance and is overfitting. Now to visualize the effect of increasing model complexity on bias and variance, let's look at the decision tree regressor. So we'll vary the depth of the tree and plot training and test error. So let me run this and let's plot the error curves. So here we have it. This is bias variance trade-off with the decision tree. So this graph will show us the U-shaped curve, right? As the model complexity increase, that is the tree depth, the training errors, this is the training error, decreases because the model fits the data better. However, after a certain point, the test error increase. Here, as you can see, the test error slightly increasing, which means the model is overfitting the training data. So this visual demonstrate how increasing model complexity reduce bias but increase variance, and it helps us to understand the bias variance trade-off in action. So now, how do we manage this trade-off in practice? Here are a few techniques you can use. So cross validation, it helps us to evaluate the model performance and reduce overfitting. Regularization, method like L1 or L2 regularization, add penalties to the model complexity and help control variance. Ensemble methods, like we have seen in the previous video, using the model sector in a forest, gradient boosting can reduce the variance while maintaining flexibility. And pruning for decision tree, you can limit the tree depth or prune unnecessary branches to avoid overfitting. So by carefully managing the bias and variance, we can build models that generalize well to new unseen data and avoid the pitfall of underfitting and overfitting. And that's a wrap up on today's tutorial about the bias and variance trade-off. I hope this one gave you a clear understanding of how bias and variance affects model performance. I will thank you for watching. I will see you in the next video.